SKM Systems Analysis located at 15,879 East Avenue Drive, Fountain Hills, Arizona 85268 can be reached at area code 480-837-8999 or by email at. Their website is www.skm.com. This company offers software for calculating fault currents and performing power systems analysis. Fault current calculation software is an essential tool for electrical engineers and technicians involved in the design, analysis, and maintenance of electrical power systems. It helps to determine the magnitude of fault currents that can occur during short circuits or other electrical faults. This information is crucial for several reasons. Firstly, it is important for selecting appropriate protective devices such as circuit breakers and fuses. These devices must be capable of interrupting the maximum fault current to prevent damage to equipment and ensure safety. The fault current magnitude determines the required interrupting rating of these devices. Secondly, fault current calculations are necessary for coordinating protective devices. Coordination ensures that the device closest to the fault will trip first, minimizing the extent of the outage. This involves setting the time current characteristics of the protective devices so that they operate selectively. Thirdly, fault current calculations are used to determine the bracing requirements for electrical equipment such as switchgear, panel boards, and bus ducts. These components must be able to withstand the mechanical stresses imposed by high fault currents. The calculations help to ensure that the equipment is adequately braced to prevent damage or failure during a fault. There are several methods for calculating fault currents, including hand calculations, computer software, and simplified tables. Hand calculations are based on fundamental circuit analysis principles and can be used for simple systems. However, they become cumbersome and time-consuming for complex systems with multiple sources and branches. Computer software provides a more efficient and accurate way to calculate fault currents for complex systems. These programs typically use iterative algorithms to solve the network equations and determine the fault current distribution. They also incorporate databases of component impedances and other parameters, which simplifies the modeling process. Simplified tables and charts can be used for quick estimates of fault currents in specific situations. These tables are based on typical system configurations and component impedances and can be helpful for preliminary design or troubleshooting. However, they should not be used for final design or protection coordination, as they may not accurately reflect the actual system conditions. When performing fault current calculations, it is important to consider several factors including the system voltage, source impedance, transformer impedances, cable impedances, motor contributions, and grounding configuration. The system voltage is the voltage at which the fault occurs. It is typically the nominal voltage of the system, such as 480 volts or 13.8 kilovolts. The source impedance is the impedance of the power source, such as a utility grid or generator. It represents the opposition to current flow from the source to the fault location. The transformer impedances are the impedances of the transformers in the system. They represent the opposition to current flow through the transformers. The cable impedances are the impedances of the cables or conductors in the system. They represent the opposition to current flow through the cables. The motor contributions are the currents that flow from motors back into the fault. Motors can act as generators during a fault, supplying current to the fault location. The grounding configuration is the way in which the system is grounded. It can be solidly grounded, impedance grounded, or ungrounded. The grounding configuration affects the magnitude and path of the fault current. There are several types of faults that can occur in electrical power systems, including three-phase faults, phase-to-phase faults, phase-to-ground faults, and double phase-to-ground faults. A three-phase fault is a short circuit between all three phases of the system. It is the most severe type of fault and results in the highest fault current. A phase-to-phase fault is a short circuit between two phases of the system. It results in a lower fault current than a three-phase fault. A phase-to-ground fault is a short circuit between one phase and ground. It is the most common type of fault and can result in a significant fault current. A double phase to ground fault is a short circuit between two phases and ground. It results in a fault current that is higher than a phase to ground fault but lower than a three-phase fault. The location of the fault also affects the magnitude of the fault current. Faults that occur closer to the source will result in higher fault currents than faults that occur further away from the source. This is because the impedance between the source and the fault location is lower for faults closer to the source. Fault current calculations are typically performed using computer software that implements the per unit method. The per unit method simplifies the calculations by normalizing all the system parameters to a common base. This eliminates the need to work with large numbers and simplifies the analysis. This software also allows for the modeling of complex system configurations and the inclusion of various types of equipment such as transformers, cables, motors, and generators. The results of the fault current calculations are typically presented in the form of a fault current report. The report includes the fault current magnitude at various locations in the system, as well as the X/R ratio and the symmetrical and asymmetrical fault currents. The X/R ratio is the ratio of the system reactance to the system resistance at the fault location. It is used to determine the DC offset of the fault current, which is important for selecting protective devices. The symmetrical fault current is the RMS value of the fault current after the DC offset has decayed. The asymmetrical fault current is the RMS value of the fault current including the DC offset. The fault current report also includes information about the protective devices in the system, such as their interrupting ratings and time current characteristics. This information is used to verify that the protective devices are adequately sized and coordinated to protect the system from fault currents. In addition to calculating fault currents, fault current calculation software can also be used to perform other types of power systems analysis, such as load flow studies, motor starting studies, and harmonic analysis. Load flow studies determine the voltage and current distribution in the system under normal operating conditions. Motor starting studies determine the voltage drop and current inrush that occur when motors are started. Harmonic analysis determines the harmonic content of the voltage and current waveforms in the system. These types of analysis can be used to optimize the performance and reliability of the electrical power system. To summarize, fault current calculation software is a valuable tool for electrical engineers and technicians involved in the design, analysis, and maintenance of electrical power systems. It helps to determine the magnitude of fault currents, which is crucial for selecting appropriate protective devices, coordinating protective devices, and determining the bracing requirements for electrical equipment. The software can also be used to perform other types of power systems analysis, such as load flow studies, motor starting studies, and harmonic analysis. Fault current calculations are essential for ensuring the safety and reliability of electrical power systems. They help to prevent damage to equipment, minimize outages, and protect personnel from electrical hazards. Therefore, it is important to use accurate and reliable fault current calculation software and to follow industry best practices when performing these calculations. Electrical codes and standards, such as the National Electrical Code, or NEC, provide guidance on fault current calculations and the selection of protective devices. The NEC requires that electrical equipment be rated to withstand the available fault current at its terminals. This means that the equipment must be able to withstand the mechanical and thermal stresses imposed by the fault current without failing. The NEC also provides requirements for the coordination of protective devices. Coordination ensures that the device closest to the fault will trip first, minimizing the extent of the outage. The NEC also provides requirements for the grounding of electrical systems. Grounding helps to limit the voltage rise during a fault and to provide a lower impedance path for the fault current to return to the source. This helps to protect personnel from electrical shock and to prevent damage to equipment. In addition to the NEC, other industry standards such as the Institute of Electrical and Electronics Engineers, or IEE, standards provide guidance on fault current calculations and power systems analysis. These standards provide detailed methods for calculating fault currents and for performing other types of power systems analysis. They also provide guidance on the selection of protective devices and the coordination of protective devices. It is important to stay up to date on the latest codes and standards and to follow industry best practices when performing fault current calculations and power systems analysis. This will help to ensure the safety and reliability of electrical power systems. When selecting fault current calculation software, it is important to consider several factors, including the software's accuracy, ease of use, and features. The software should be accurate and reliable and should provide accurate results for a variety of system configurations. The software should also be easy to use and should have a user-friendly interface. The software should also have a variety of features, such as the ability to model complex system configurations, the ability to include various types of equipment, and the ability to perform other types of power systems analysis. It is also important to consider the software support and training options. The software vendor should provide good support and training to help users learn how to use the software effectively. In conclusion, fault current calculation software is an essential tool for electrical engineers and technicians involved in the design, analysis, and maintenance of electrical power systems. It helps to determine the magnitude of fault currents, which is crucial for selecting appropriate protective devices, coordinating protective devices, and determining the bracing requirements for electrical equipment. It is important to use accurate and reliable fault current calculation software and to follow industry best practices when performing these calculations. Electrical codes and standards, such as the NEC and IEE standards, provide guidance on fault current calculations and the selection of protective devices. By following these guidelines, electrical engineers and technicians can ensure the safety and reliability of electrical power systems. The accurate calculation of fault currents is paramount for ensuring electrical safety and system reliability. Protective devices, like circuit breakers and fuses, are selected based on their ability to interrupt the maximum prospective fault current. An incorrect calculation can lead to the selection of underrated devices, resulting in potential equipment failure, fire hazards, and personnel injury. Coordination of protective devices relies on accurate fault current calculations. Selective coordination ensures that only the protective device closest to the fault trips, isolating the faulted section while maintaining power to the rest of the system. Incorrect fault current values can disrupt this coordination, leading to widespread outages. Equipment bracing, particularly in switchgear and panel boards, is designed to withstand the mechanical forces generated by high fault currents. Accurate fault current calculations are essential to verify that the equipment bracing is adequate to prevent structural damage during a fault. Several factors influence the magnitude of fault currents. System voltage plays a direct role. Higher voltages generally result in higher fault currents, assuming other parameters are constant. Source impedance, which represents the impedance of the power utility or generator supplying the system, limits the fault current. A lower source impedance allows for higher fault currents. Transformer impedances restrict fault current flow, with lower impedance transformers contributing to higher fault currents. Cable impedances also limit fault currents, with longer and smaller cables having higher impedances. Motor contributions can significantly increase fault currents, as motors act as generators during a fault, feeding current back into the system. The grounding configuration, whether solidly grounded, impedance grounded, or ungrounded, affects the magnitude and path of fault currents. Different types of faults also result in varying fault current magnitudes. Three-phase faults are generally the most severe, resulting in the highest fault currents. Phase-to-phase faults have lower fault current magnitudes than three-phase faults. Phase-to-ground faults are common and can result in significant fault currents, depending on the grounding configuration. Double phase-to-ground faults have fault current magnitudes between those of phase-to-ground and three-phase faults. The location of the fault within the electrical system also affects the fault current magnitude. Faults closer to the power source generally result in higher fault currents due to lower impedance between the source and the fault. Fault current calculation software typically employs the per-unit method to simplify calculations. This method normalizes all system parameters to a common base, making the analysis easier to manage. This software uses iterative algorithms to solve network equations and determine the fault current distribution throughout the system. Fault current study reports typically include the following information: the symmetrical fault current, which is the root mean square or RMS value of the fault current after the transient direct current or DC component has decayed; the asymmetrical fault current, which is the RMS value of the fault current including the DC offset; the X over R ratio, which is the ratio of reactance to resistance at the fault location and is used to determine the DC offset; the interrupting rating of protective devices, which indicates the maximum fault current that the device can safely interrupt; the time current characteristic curves of protective devices, which show the relationship between the current and the time it takes for the device to trip. Software such as SKM can perform various other types of power system studies, including load flow analysis, which determines the voltage and current distribution in the system under normal operating conditions; motor starting studies, which analyze the impact of motor starting on the system voltage and current; transient stability analysis, which assesses the ability of the system to maintain stability following a disturbance; harmonic analysis, which identifies and quantifies harmonic currents and voltages in the system; arc flash analysis, which calculates the incident energy and arc flash boundary associated with electrical arcs. When selecting fault current calculation software, consider its accuracy and reliability, user-friendliness, modeling capabilities, reporting features, and compliance with industry standards. Ensure the software is regularly updated to incorporate the latest standards and calculation methods. Consider attending training courses or workshops to enhance your understanding of fault current calculations and the use of fault current calculation software. Regularly review and update your fault current studies to reflect changes in the electrical system. Ensure that all protective devices are properly sized and coordinated based on the results of the fault current studies. Always prioritize safety when working with electrical systems. Use appropriate personal protective equipment or PPE and follow safe work practices. Compliance with relevant electrical codes and standards is essential for ensuring electrical safety and system reliability. The National Electrical Code, or NEC, Article 110.9 addresses interrupting rating and requires equipment intended to interrupt current at fault levels to have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment must be suitable for the maximum available fault current. NEC Section 110.10 addresses circuit impedance, other characteristics, and fault current ratings. The overcurrent protective devices, the total impedance, component short circuit current ratings, and other factors shall be selected and coordinated to permit the circuit protective devices to clear a fault to limit the damage to electrical equipment. NEC Section 230.82 Exception Number 3 addresses equipment connected to the supply side of the service disconnecting means and tap connections ahead of service equipment shall be installed so as to be protected from physical damage using suitable electrical enclosures or other methods approved by the authority having jurisdiction, ORG. NEC Section 240.86 details that a circuit breaker with series combination rating shall be permitted only where tested and listed as a series combination in compliance with UL Standard 489. The marking requirements of UL 489 outline the short circuit current ratings of circuit breakers. IEEE Standard 1584 provides equations and methods for calculating arc flash incident energy and arc flash boundaries. The standard provides guidance for performing arc flash risk assessments and selecting appropriate personal protective equipment.